Hi everyone, this is a video presenting experimental results for our paper Distributed Consistent Multi-Robot Semantic Localization and Mapping. Our approach is a multi-robot distributed semantic SLAM approach in which we maintain a hybrid belief, we use a viewpoint-dependent classifier model, and we avoid double counting for both continuous and discrete random variables. In our experiment setting, we have 6 identical shells within the environment. Both we get geometric measurements and semantic measurements from them, and we train a viewpoint-dependent classifier model for each and every 3 of the candidate classes that we have, with communication range of 3 meters. We have 3 separate classifier models. Each is assumed Gaussian with parameters that are spatially dependent. And we show here in the graphs the expectation based on spatial parameters, which are yaw angle and pitch angle. The first is for class 1, then for class 2, and finally for class 3. Now we present the notations for our SLAM graph. We have the green dot and the yellow-green marker that present the ground truth, object pose, and orientation. We have the pose estimation with the black and gray ellipse for the object poses and the red ellipse for the robot poses, and we have the ground truth poses in the red and blue mark. The ground truth path can be one of 3 colors. It depends on the robot that we use. Can be green, blue, or red. Also, we have a communication graph that presents the communication between robots. The communication is mutual. For classification scores, we use a bar graph, which a bar for each and every object. The bar itself can be blue, representing class 1, which is the ground truth as well, orange representing class 2, and white representing class 3. Now we present the experimental results for the case where the robots don't communicate between each other. This is divided by 3 columns, and from left to right this is robot 1 to 3. And you can see in the bottom row the classification, especially for robot 2, is not very accurate for some of the objects. Now in the second case, where the robots do communicate between each other, where we use a full algorithm, you can see that first of all, the estimation accuracy increases, the estimation covariance reduces, the coverage of each robot, the amount of object that it sees increases. You can see also that the classification accuracy increases with time and the communication between robots. And the classification scores are getting pretty much similar because the robots communicate between each other and the state gets closer between each other. Now we show graphs that were also presented in the paper. We compare between the cases where robots don't communicate between each other, where we do have double counting, and when our full algorithm is activated. So we compare localization accuracy in the first graphs. In the next, we present the measure for estimation covariance, and the third, we use a metric to show how much our classification results are accurate. We use the MSDE metric for for that.